So we left out on the fascinating parts of production. So let's go ahead and get back into it. So the cool part about production is we're thinking about what inputs, the labor and the capital, are we putting together to be able to produce a good or service? And when does it make sense to no longer hire an additional worker or no longer hire or purchase an additional machine or oven or whatever else, right? So we need to think about how we're employing the right level of inputs. We're keeping it very, very basic in this class. Our only two inputs are capital, the non-human elements of being able to produce something, and labor, the human workers, right? Your unit of labors, they can be by hour, they can be by person, they can be by whatever else. But let's assume for the next example that it's by person. So I'm wondering what the marginal product of labor is for one more person. How much does the total product being produced by this business increase when I bring in one more person? So let's say that I have a ceramic shop because I have a cute coffee mug in front of me today. So I'm just kind of basing it off of that. We have a ceramic shop. So when I had 4 workers, maybe we were producing 65, right? Now that I brought in a 5th worker, we're a little bit more productive. I mean, we're not a lot more productive because we still have a certain amount of machines, but when we bring in that 5th worker, let's say that we now produce 70 mugs. Well, then that means the marginal product of labor for that extra person is the 5 additional mugs that my business is now producing. What can I sell them for? What's the value for that additional worker? Well, it's the 5 mugs that they purchased times the price of those 5 mugs. So let's say we have the 5 mugs, maybe they get sold for $10 each. That is $50, right? Okay. Well, if we have this increase in total product and the amount that we can sell it for, it's $50, we need to think about, okay, well, what is the wage rate of that employee that we added? If we needed to pay them $50 for the day to make those 5 mugs, then that's equal. That's the last worker that we would hire. If their wage rate is maybe $40 and they're still producing a marginal product that their price and the value of it is above that amount of the wage, we might even consider bringing in another worker. While if it's below, for example, we're making $50 selling these additional mugs, or the additional mugs from total product, because we have this worker, but we have to pay the worker $100. Well, if we're making 50 and it costs us 100, that's no longer a good deal. So we need to think about the marginal product of labor and the value of the marginal product of labor in terms of the prices and wages, right? So essentially the value of the marginal product of labor needs to equal the wage rate. We just call that little W, right? So actually you can see that right here, just a little bit of W. I'll show you on the graph what that means in a little bit once we kind of talk through the basis of this. So much like we have the marginal product of labor, the additional amount to total product that we might have from one more worker, we also have similar for capital. So we have the marginal product of capital. For example, if in my ceramic studio, we had 3 of the little pottery wheels as opposed to 2 of the pottery wheels, how many more mugs can we now produce? Assuming we always have the same number of workers. Well, maybe our total product increases by 10 when we have a new pottery wheel. Well, that's pretty cool. That's pretty neat. Okay, so 10 mugs. What does that mean at the end of the day? If those 10 mugs can be sold for $10, then that means that the marginal product of this capital, the value of the marginal product of capital times the price that we can sell them for, those 10 mugs times $10 means that is $100 extra that we get because this additional piece of capital exists, holding the number of laborers fixed, right? So we need to think, is that $100 a good deal or not? As many of you know, machines are expensive, it turns out. The wage, or ideally wage when it comes to capital, is the idea of rent. What could you have rented out that pottery wheel for? If I wanted to instead rent it to the ceramic studio down the road, what would they have paid for it? If I instead wanted to put that money into investments, what would have been made on it? With the other next best uses of that money, what would be the ideal rent that I would have gotten for that same amount of money that I am instead putting into this machine? So let's say that the rent for the machine, if I had rented it out to a ceramic studio down the road, is $125. Well, if the price times the marginal product of the capital for that 10 ceramic mugs at $10, that $100, that $100 is less than the $125 that we need for rent. At that point, I would not employ that piece of capital, right? But what if it instead was, we have this additional $100 from the increases in total product times the price. And maybe the rent for this pottery wheel is $50. Well, then that's a great deal. We're very happy with that. We might even consider a fourth pottery wheel after that. If the rent is $100 and the amount that we're getting in with the changes in total product times the price is $100, then we're good. That is the last bit of capital that we will employ, right? Because the value of it is equal to the additional revenue from the additional amounts that it's making. Okay, so that's kind of a guideline to the production process and why we would make these sort of decisions. So now we need to think about how do we graph that, right? So there's two main things that we need to consider. One is the quantity of what we're producing. How much are we going to be producing? The second part we need to think about is the cost of that production, right? So the cost of that production is what we just talked about. It's the idea of every laborer we have, there's a wage rate for them, right? That's money that we are spending. For every piece of capital we have, there's rent that we pay. There's an amount that it costs to maintain that piece of capital that we need to think about. So actually, let's go ahead and start drawing out one graph so we can think about what this is going to be. It's going to look similar to the consumer behavior, but this is actually very different. This is dealing with the production part of the process. So let's say, for example, that we have, oh gosh, if I can draw today. So let's say that we have our graph. And let's say that across the top, maybe let's have the amount of capital, right? So let's just call this machines. It's a little bit easier to think of 1 machine, 2 machine, 5 machines. And then let's down here, let's have the number of workers, i.e. the amount of labor, right? So there's going to be some amount of production that we can make with some combinations of those, right? And let's maybe talk through an example. Let's say that we had 1 worker with 100 machines. Well, if we have 1 worker with 100 pottery wheels, like, yeah, maybe they can have a couple projects going on, a couple different ones of them, but they're probably not producing all that much, right? You're still limited by the number of workers. So let's say that we're right here. Lots of machines, lots of workers. Or very little workers, lots of machines. Then there might be some point in the middle where like, hey, maybe we have some machines and some workers, and we got 1 worker sitting at every machine, and that seems to be a pretty good balance. Or we might have another case where we have almost no machines, but lots and lots of workers. Okay, well, if we have 30 people in the ceramic studio, but only 2 pottery wheels, they're not going to be able to be that productive. So let's kind of put these together. And here, we'll just put it out this way. Let's call this an iso-quant line. Iso-quant. Iso-quants are different levels of production, right? Let's say in this case, maybe they can produce 10 ceramic mugs, right? You can either have 1 person running a whole bunch of machines, maybe they can do 10. Maybe we have 2 machines and a whole bunch of workers, maybe together they can make 10, or somewhere in the middle. Maybe we have 3 or 4 workers with 3 or 4 pottery wheels and they can produce 10. These are the different combinations that make this level of output, right? So like when 10 equals Q. Or no, they are going to have parallel preferences outwards, right? So let's say that maybe this line is some combination where they can, some combination where maybe they can make 20 mugs. Maybe you can have this many machines and workers or this many machines and workers. But along this line with all of these different combinations of input, they can make the same level of production. So on and so forth. Maybe this is Q equals 30. Notice that we are going outwards from this intercept. And these are just our iso-quant lines. Now, sometimes they look like this, where they're slightly bowed. Sometimes they'll be closer to a straight line, and sometimes they'll be closer to an L. We'll talk about those 3 different situations, but what I need you to keep in your mind right now is the idea that iso-quant lines are different levels of production. So each line represents, okay, I can make 10 here, or I can make 20 here, or I can make 30 here. And it's the different types of combinations in between our machines. So let's say our capital input and our workers, our labor input that can get that level of production. All right, so we need to think about this efficient allocation by also including the cost of the production. So the cost of production is going to be equal to the money that's spent on it, right? Cost is a combination of the amount of laborers times the wage that you pay them plus the amount of capital that you have times the rental rate of that capital. So we'll show you that in a minute. Let's talk about the isoquant curves. I don't want to confuse anybody too far. Once we get through the isoquant curves, and then we'll add in the ISO cost curves that are going to be looking at the relationship in between wage and rental rates. Okay, so with isoquant curves, these are just the combinations of inputs, right? So it's one of these little curves represents all the different ways that we can make that level of production, right? That yield the same amount of output. They have the same Q if they are along the same line. The shape of an isoquant reflects the ease at which a producer can substitute among inputs while maintaining the same level of output. So our goal is to find the lowest cost point on an isoquant. We want to figure out how we can make the most amount of stuff for the inputs that we have, right? So the slope of the isoquant, this is the rate at which two inputs can be substituted for each other. We call this the marginal rate of technical substitution. Let me show you in a graph what that means, because this is going to be very confusing, and I want to make sure that we kind of get this off the bat, because this is one of the more difficult concepts in economics to understand. This one gives my senior undergrads a little bit of pause. So let's say that we have three different situations. Let's look at the first one. This is the one that we drew above, where we might have some sort of curvature. So let's say this is Q equals 10. This is our capital input and our labor input. And let's say that we're making ceramic mugs. We can either have lots of capital and very little workers, or a little bit of capital and lots of workers, or some combination between the two, right? And then we go forward and we have different levels of production. Now the slopes that we have here, the tangent lines of the slopes at each of these points, represents the marginal rate of technical substitution. What that means is, notice when we're all the way up here, all the way up here, if we were going to get rid of one worker, we would probably need a lot of additional machines to make up that amount of goods. What if we're down here? Well, if we're down here and we are giving up a machine, we might have to add a lot of workers to make up for the fact that we no longer have that machine. The differences here are just relative to the slope, and the slope changes depending on where we are within the graph. So this one is just a very nice, easy one, but let's see what two different extreme examples would be. So let's say instead we're at a point where we can only produce, or well, we can produce different levels, but maybe you really have to use two inputs together. So we have to have one worker per pottery wheel. We can have more pottery wheels, doesn't matter because the worker can only use one. Or we can have more workers, doesn't matter, it's equal to the number of pottery wheels. Maybe we need exactly one pottery wheel per worker. Well, then we might instead have isoquant curves that look like L's. Let me show you what I mean by this. Let's say this is Q equals 10, and let's say this is Q equals 20. That means at this point where maybe we have, let's say, one pottery wheel and one worker, they are able to produce 10 coffee mugs. If you have, for example, two machines, but you still have that one worker, notice that you are still producing only 10 coffee mugs. Or likewise down here, let's say that you have two workers, but one machine at this point. Well, that doesn't do you any good either. You can only produce 10 coffee mugs because maybe you need one person per machine. Let's say that instead we multiply both. So instead of adding in a pottery wheel or a laborer, we add in both a pottery wheel and laborer. So we start to go up here, right? Then we're going to locate at this point right here. So if we have two pottery wheels and two workers, maybe we can produce 20 of something. Now we're not able to add a third pottery wheel if we only have two workers because it won't increase our amount of production. We will still be producing only 20. While here we might, if we have, for example, 3 laborers but 2 pottery wheels, we might still only be able to make 20 because it's one person to one pottery wheel, right? So this is the idea of a Leontief ISO curve. Well, let's Leontief ISO quant curve. I like to remember it because Leontief, and don't worry, I write it in the slides, so you do not have to worry about my terrible spelling and the fact that my handwriting looks like chicken scratch. It turns out the more degrees you have, the worse your handwriting gets. I used to have really pretty handwriting, but every year it gets worse. Anyways, Leontief starts with an L. That's kind of how I remember that it's this one, because these iso quant curves are shaped like an L. Now we have the other extreme, right? That's the idea that like you have to have one pottery wheel, one person. But what if we were at the other extreme where I'm making pottery and it's either the wheel can do it automatically on its own or a worker can do it automatically on its own? Doesn't really matter. Well, then our iso quant curves might look something more like this. Where, oh, I thought I turned my phone off, so sorry if you're hearing it going. Maybe Q equals 10. Maybe we can make 10 by using only machines right here. Oops. Or we can make 10 by using only labor right here. Or we can either increase capital or labor and make maybe Q equals 20. In this case, when we have these flat ones, we know that these are pretty much substitute factors of production. So the closer we get to having a flat line, these are ones where we're just going to go for whichever one's cheaper. If one machine can make my ceramic mug or one person can make my ceramic mug, then I'm going to just employ whichever one is cheaper. If the machines are cheaper, get machines. If the worker is cheaper, get workers. In Leontief, that's the idea of having a relationship that's kind of stuck together. They have to be used together. They're not substitute inputs of production. They're complementary inputs of production where you have to have the two together. Then it looks more like an L. The closer you are to an L, the more strict you have to be about this relationship of having 1-to-1, 1-to-2, something like that, right? So in the middle is this idea of this curved line. Iso quant curves can come in lots of different shapes and sizes. Now, again, the slope in between them, that's the marginal rate of substitution, right? So, or technical substitution. So we see right here and right here, we kind of talked about this. These slopes, marginal rate of technical substitution, MRTS, this is just equal to the marginal product of labor. So how much additional stuff we get from labor. So see it moving towards the right. How many additional things might be created as we add a worker, divided by the marginal product of capital. So how many additional things do you give up when you're giving up capital, right? So the marginal rate of technical substitution is just, oops, MRTS, the relationship in between the two. Now, they kind of change in this curvature line, while in the other two, in Leontief and isoquant, notice that they're kind of set. So it's either you have it at this degree angle or they are relatively flat. If they're relatively flat, then that means that it makes no sense to add additional workers, right? The idea, if we have one pottery wheel and one worker, don't add another worker. While over here, they're a little bit more aligned to exactly where the curve is, saying you choose whichever one is cheaper. If you do not remember calculus, do not worry. We will figure this out and we can get through it together, because a lot of the time, the way that you would figure out the marginal rate or the marginal product of labor and the marginal product of capital is to just take the derivatives and then put the first derivative over the second derivative, divide it out, and you get your marginal rate of technical substitution. I'm not going to make you do that because that's a lot of work. Yeah, sorry. If you really want to do the calculus, you're more than welcome to take the other 528 course, or just ask me. I am more than willing to teach you the calculus too. So we have different forms of isoquants where they just have these different shapes. Do they look more like an L, or are they more of a flat curve? So this depends on if capital and labor are substitutes or complements. If the capital or labor are considered substitutes, I can use one or the other to make a good, then it's going to be a flat line. If they're considered complements, I need to use them in tandem to be able to produce something, then that's the one that looks more like an L, and we have to have this set relationship of maybe one worker to one machine or one worker to two machines, but some sort of set relationship that has to be continued. So those are the two extreme cases, and Cobb-Douglas is more of that sloped one, right? The one that's not an L, it's not flat, it's kind of a curve in between the two. So those are more of the two extreme cases, and then let's kind of go back to the idea of Cobb-Douglas at the end of that. So linear isoquants. This is the case where capital and labor are perfect substitutes for one another. The amount that you are making is equal, instead of, here. Let's go back to OneNote. In this case, this is our Cobb-Douglas production function, right? This is Q, or Q is equal to some amount of capital, 2 in alpha, times some amount of labor, 1 minus alpha, where these equal out to 1, right? Instead, when we have, oh, I should have marked it up here, linear isoquants, when we have this very flat arrangement, we end up just choosing whichever one's cheaper. So the amount that we produce, Q is equal to some, let's call it A, right? Some A of capital, so your capital investment, plus B of labor, right? In this case, the marginal rate of technical substitution, if we take the derivatives, which you don't have to, because I'm just going to tell you what it is B over A. That's just the slope of this line. For every single amount of K that I have to give up, we're going to consider that like A. We're going to get some amount of B that we have to put in to produce that same amount. We have to switch in between the two. And our marginal rate of technical substitution is just equal to what the slope of that line is going to be. So linear isoquants imply that these inputs are, here, let's put it up here, substitutes at some sort of constant rate. So it's not that I'm substituting them 1 for 1, and then once I get really, really low on something, I start substituting them 1 for 4. These are ones that are always substituted at the same rate, and that rate is B over A. All right, so after that, so we have the linear case. Let's talk about the Leontief case that I mentioned. This is the one where the amount that you can produce is going to be dependent on whatever the thing that you have the least amount of is. Right? So this is the case for capital and labor. They might be perfect complements. You have to use them in tandem, 1 to 1 or 1 to 2 or whatever else the ratio is, but there is some set ratio you have to keep. Adding more of only one of the inputs is not going to increase your output. You have to add more of both if you wanted to increase output. So capital and labor are used in some sort of fixed proportion. Let me show you what that means. So that means in Leontief, that we might have the case where if we're right here, we have to add some of both goods to be able to increase the production. To go from Q equals 10 to Q equals 20, we'd have to add more of both inputs. If we add only, for example, capital, well, then that's very difficult because adding only capital does not help with the fact that we need more labor to sit at those pottery wheels to be able to produce more ceramic mugs, right? So our function in this one is just Q equals the minimum. So whichever one we have the least amount of, right? Of, let's say, BK and CL. So B and C in this case just is sort of the rate that you can switch it off from. In this case, it's 1 to 1. Sometimes it might be 1 to 2, 2 to 1, so on and so forth. So if we have a 1 to 1 relationship, then if we have 3 capital inputs and 1 labor input, then we are producing only 10 mugs because the minimum amount or the one that's kind of binding us to this Q equals 10 is the fact that we have 1 laborer, right? If we instead have 3 capital and 2 laborers, well, in that case, notice that we would be right here. We would still only be producing 20 because we are bound by whatever that amount of labor is, even if we have more capital. It's whichever one is minimized, that's the one we're stuck at, right? So here we have, our Leontief, our linear. Under Leontief, let me just go ahead and put complements, because these are complementary inputs. They have to be used together. Linear, they can be used either way. Cobb-Douglas, let's go ahead and put the name up here somewhere. Cobb-Douglas, it depends what the proportion is. So up here, when I have a ton of capital and almost no laborers, then adding 1 laborer, even if it costs me a whole bunch of machines, is going to matter a lot, right? And that's how we're going to move along that curve. Okay, now I wonder if y'all are getting like Calc 2 flashbacks at this point. So on the Leontief, since capital and labor are consumed in some sort of fixed proportions, there's no input substitution along the isoquant. There's no marginal rate of technical substitution in between 4 laborers and 1 machine and 3 laborers and 1 machine, right? You're still producing the same amount of goods. Then we have the idea of the Cobb-Douglas production function. This is one where it's the marginal product of capital over the marginal product of labor. So I have that up here, right? Oh, hold on. My slides are wrong. Why are my slides wrong? Let's go ahead and go back and fix that. I'll go online and fix this for y'all later. Sorry about that. All right, so it's just looking at this relationship in between the marginal product of labor and the marginal product of capital when we're going along that sloped line. Okay, and if y'all want more examples of that, please just let me know and I can make them for you too. Okay, so with that, let's go to the next part. Let's pause right here, because right now you're probably like, wow, this is complicated, right? Like, let's look at, oh my gosh, there's all these different graphs and we have to think about like all these different ways to produce goods and services, but that's only half of the equation, right? It's only half of what we're interested about, because we are not only interested in what we're producing, but at what cost points can we produce it at? The goal is to produce things along the isoquant curve, so efficiently, right? We would like to do things efficiently for as low a cost as possible. So we can figure out where this point is, where we are producing things for as low a cost as possible using an ISO cost curve. So we learned about isoquant. Let's put together the idea of ISO cost. So actually, let's go back and we'll talk a little bit about this graphically before we go into what the definitions are going to be. So ISO cost lines. Here, first, actually, let me put back up our isoquant so that we can just kind of look at it at the side. Notice that we have some sort of change in between capital, labor. There's some level of production, so let's call this Q1, and there might be higher levels of production Q2 as we're moving outwards and adding in more of the different inputs, right? ISO cost, so this is isoquant. ISO cost is looking at the cost relationship in between the two. So this is instead going to be looking at our relationships in between capital and labor and those different rates that we have to pay them. So remember that we have a wage rate for capital. If I could draw today, please just pretend that this is a K. So we have some sort of relationship in between that wage rate for laborers and that rental rate for capital. So let's think about what this would mean. So ISO cost is what can we afford, right? There's some amount that we need to pay capital, which is equal to the wage, or excuse me, labor is equal to the wage, while capital is equal to the rent. So what we do know so far is the equation that I showed you earlier. Oops. And that's going to be that the total amount of cost for whatever we're producing is going to be equal to the wage that we're paying our laborers, so WL, plus the rental rate times capital. So the amount that we're kind of paying for this capital times the amount of capital that we have. So let's rearrange this, because we need an equation where we can talk about one good in terms of the other good. So let's figure out what it would be if we have to just have K equal to something. Well, if we have K equal to something, let's see, that would be, actually, let's put RK over on this side. If we have RK over on this side, then we know that we're going to have C minus WL, right? Am I going crazy? No, that looks right. That looks right. Okay, minus WL. So if we divide by R, we're going to have K equal to C divided by R minus WL divided by R. Okay, simple enough. So this means for a given level of capital, right? For a given level of capital, it equals some amount of total cost divided by that rental rate you have to pay for the capital minus the wage for labor divided also by that rental rate. Okay, that all seems very complicated. What it basically boils down to is for a given input price, the ISO cost furthest from the origin are more expensive. So what we basically have is like right here. Let's say that this might be ISO cost C. For some amount of total cost C, maybe we call that $100. This is the amount that we can produce. Maybe we continue on out. If we spend all our money on labor, right? Then what that means is that the total amount that, or if we spend our total cost on labor, then we're going to have whatever that cost is, divided by that wage rate. That's the number of laborers that we're going to be able to purchase. That will be this input. Over here for capital, if we spend all of our money only on machines, please stop. There we go. Then it's going to be our total cost divided by that rental rate of capital. And there's going to be some sort of combinations in between them. So maybe this is C2. Maybe this is everything that we can produce if we have $200 and the different combinations of it. If we have $200, we can put all of our money into capital, or we can put all of our money into labor, or some sort of combination in between the two. Notice that these ISO costs are just parallel increasing linear functions, right? And they're going to have a slope in between them. This slope is going to be relative to what we are producing. So when we think about the trade-off in between capital and labor, what do we really mean? Well, if we give up one capital input, what we really give up is some amount of payment for that, right? So maybe we call this minus R. And if we were to trade that instead for labor and we paid labor instead, then we would gain W. That means that this slope is a relationship in between, it's a relationship in between the wage rate and the rental rate. So let's just call this slope equals what? Minus W over R. Okay, which means we have a downward slope. It's going downwards by some rate relative to the wage and rental rate. Oh, I'm getting so tongue-tied today. So we have our ISO quant curves and our ISO cost curves. Let's have a slightly cleaner one right here to see what they would look like together. If we have a given ISO quant, so let's say Q10, we're going to want the ISO cost curve that touches this only once. So let's say that we have ISO cost curve C1, C2, C3. Well, at C3, we can produce this amount of good, but notice that it's not necessarily efficient because it touches twice. And maybe this could instead hit, I don't know, let's say Q20. If we had either this point, let's call it C and A, or C and A, we'd say this may not be the most efficient way to do it because there might be some other amount of production that we can have at the same cost curve, maybe point B, that would be more efficient for us to operate at. So the ISO cost does not make sense unless we are at a point that is tangent. We're wanting the point where the ISO cost curve and the ISO quant curve have the same marginal technical rate of substitution, or marginal rate of technical substitution, maybe right here at point D. Notice that it's the point where this ISO quant curve touches the ISO cost curve only once. And if we took the derivative of the ISO quant curve, which I'm not going to make you do, but just so you know, if we took the derivative of the ISO quant curve, they would be equal right here. And that is super freaking cool. That is neat because it tells us a few very important things. It tells us if we have an amount of money that we can spend to employ workers, so our labor, and to pay for capital, K, we can figure out what distribution in between the two will be able to maximize the amount that we can produce for the lowest cost possible. And I just love that. That's neat because this is putting together that production side and that cost side that we were trying to figure out how to put together, right? So for a given input, for prices, ISO costs further from the origin, are more expensive. Oh no, don't do that. I don't know why it just put us forward a whole bunch. Anyways, doesn't matter. So increases in all costs versus increases in one cost are things we have to think about. Are we going to increase all costs and move forward? Or are we increasing the cost for only one good? Well, then that might be something that shifts the line one way or another. Hinges it outwards or hinges it inwards. Oh, so when we think about cost minimization, what are we wanting to know? Okay, so we know that we have a marginal product per dollar spent. If we put $1 into labor, there's some amount that they can produce for that wage rate, and we're wanting it to be more than that $1. If we're putting it into capital, we're wanting it to be a productive piece of capital. So the marginal product of capital, the changes in the total amount that they're producing times the amount they can sell it for, we need that to be valued more than the $1 we put into that input. That relationship in between the marginal product of labor and the marginal product of capital is actually equal to the wage over the rental rate. So that means when we're thinking about right here, this point, point D, here we go. This point right here, there's something very, very special with that. And it's the fact that the marginal product of labor over the marginal product of capital at this point is equal to that slope, right? The tangent line for D, when we take those derivatives, is going to be equal to the slope of the isocost curve. And the slope of the isocost curve is just equal to this way, or the wage divided by rent. Now you're probably wondering where this minus goes. It's technically because we have a minus on this side and a minus on that side. So we're just going to ignore the fact that both of them exist at this point. But what we're going to have is that the marginal product of labor and the marginal product of capital just equals the wage divided by rental rate. And oh my gosh, that is so cool, because all together, what does this necessarily equal? The marginal rate of technical substitution for labor and capital. Yeah, we figured it out. And all of this is just a very, very, very fancy way of saying we want to find where the slopes equal each other, because at that point we are being efficient. We are maximizing the amount that we can produce for the lowest cost possible, and we are maximizing the use of the products, right? And we're not just producing in the attainable zone. We don't have 10 workers and 10 machines to produce only one item. We are maximizing the use of them and being cost effective at it. So that is just so freaking cool, and I think it's just the neatest. So that's probably overwhelming. Let's go through a couple examples together that I think might be able to highlight what we're talking about when we're wanting to look at the relationship in between the two. So let's actually draw this out. Okay. So we have a couple things right here in this equilibrium that I'm going to show you, and we're going to graph through it and then we're going to talk about it together. So we know that we have some production by a Cobb-Douglas production function. Notice we know that it's Cobb-Douglas because we see that the alpha is equal 1. We have Q equals K to the 0.5 times L to the 0.5. We also know that we have a cost function. Cost functions are always the same. It's some sort of cost equal the wage times labor plus rate times capital. All right, so let me give you a couple numbers and then we're going to solve it out. We're going to figure this out. We're going to say that the cost is 200, the wage is 50, and the rental rate is 20. Okay, so let's work this example. Let's start it all out by thinking, what are we really trying to find? Well, we know it's a Cobb-Douglas function. So we know this difference in between our capital and labor, that we are going to have some amount of Q right here, and we're going to have some function that we are trying to find where it intersects, right? And this function is the cost function. So we got our isoquant curve, we got our isocost curve, and we're going to figure some things out. So we know that this Q right here, this is determined by Q equals K to the 1/2 times L to the 1/2. We also know that this cost line, because we already know what the amount of cost, or the cost line equation is that it's going to be the wage times the amount of labor plus the rental rate times capital. And then let's go ahead and do the other things that I gave you. So I gave you that the total cost that we can spend is 200. This is the amount of money that the firm has to be able to spend. We know that the wage rate, what did I say the wage rate was? Okay, I said the wage rate was 50. So these individuals make $50 an hour, or we can rent out our capital for $20 an hour. All right, let's go ahead and get through it. So if we have this information, where are we going to start? Well, the reason why we like Cobb-Douglas production functions is because it has one really cool attribute to it. And that's the fact that the marginal product of labor over the marginal product of capital is going to be equal to one very unique set of inputs, in that it's going to sort of be equal to what you'd have to give up for it. So what that essentially means is the marginal product of labor here is going to be equal to the wage rate that we're going to pay over the rental rate. So the wage rate equals the rental rate. Now, marginal product of labor over marginal product of capital. This also equals one other thing that's kind of important to know, and that's the fact that in Cobb-Douglas and Cobb-Douglas only, this also equals K over L, because the marginal product of labor is going to be equal to sort of what we could have gotten from having another capital input, because that's what we're deciding in between, is how much capital input do we give up for each additional labor input, how much labor input do we give up for each additional capital input, and what does that mean for the isoquant that we're on. So we have capital of labor equals wage over R, or rental rate. So we know a couple things here, right? Let's go ahead and start plugging stuff in. So if we have K over L, well, we know the wage. We know that the wage rate is 50, and we know that the rental rate is 20. Well, let's go ahead and cross multiply. So we know that 20K equals 50L. Let's go ahead and divide both sides by 20, just because we want to clean it up a little bit. And we know that K is equal to what? 2.5L. This gives us a relationship that we can start plugging into different functions, because notice we have two equations up here that use K and L that we have this information in between, right? Okay, so what's the next thing that we're going to want to do? Well, the next thing that we're going to want to do is kind of understand the cost function. So we know that cost equals wage L plus RK. Well, notice we now have three pieces of this equation plus a relationship. So we know the total costs, I gave you that, it's going to be 200. We have 200 to spend. And then this is going to be equal to $50 times some amount of labor plus $20 times some rental rate. Well, we know that the K, right, or the $20 rental rate times the amount of capital, we know that the K is equal to 2.5 labor. We're going to, our one machine is kind of equal to 2.5 labor hours. So let's have this multiplied by 2.5L. All right, well, let's multiply that out. So 200 equals this 50L plus 20 times 2.5 is 50L. 200 equals 100L. L equals 2. So, all right, we know the amount of labor inputs that we're going to want when our cost is 200 and we have a wage rate of 50 and our rental rate of 20 is going to be 2 workers. 2 workers is great, and we're very happy with that. Okay, well, then let's go ahead and plug that back into the equation that we had earlier, right, where we were looking at this relationship in between labor and capital. If we wanted to know our capital, because now we need to know our K, oops, let's plug this back in. I don't know why I can't write K today, but apparently I can't. That's just going to be 2.5L. So it's going to be 2.5L. So K equals 2.5 times 2. K equals 5. All right. So from all of this, what were we able to figure out? We figured out that we would want 2 laborers. So actually, 1, 2, let's just imagine this lines up, right? So let's say that this is 2 laborers. And we're going to want 5 machines. Boom. Real easy, right? 5 machines, 2 laborers. And at that point, we get to the point where we are hitting the most amount that we could possibly produce. We know this because we have that this MPL over MPK is just equal to K over L for Cobb. Let's just call it CB for CD, Cobb-Douglas. Cannot write today. So we know that we have this relationship, and when we equal it out to the cost function, this is what we get to. Have 2 workers, have 5 machines. Boom. Super easy, right? So for all that math, all that scariness, it's actually not that scary at the end of the day when we start to think about what they mean, or what they mean in a very implicit and technical way. All right, so changes in wage and rental rates can be affected by the slopes of these curves. So if, for example, there's a very, very drastic slope, if the rental rate for capital was extremely low compared to the cost of labor, we might have a line that is much sharper, right? It might have a much steeper slope. If we have a steeper slope, then we might instead prefer more machines and less workers. If we have a very flat slope, so for each machine we give up, we can afford lots and lots and lots of workers, then we might prefer a situation where we have lots of workers and a few machines. Our preferences are going to change depending on the slope of that ISO cost curve. Oh, all right. So let's start thinking about cost analysis. What does it really, really mean to sit down with these cost functions and figure out what is the most productive way to be able to do things, and what that cost truly means? Producing one more of a good or service, what does that mean for the cost of the good or service and for the amount that we can produce. And what does that mean relative to the wage, to the rental rate, and all these other pieces? That's a lot of moving parts. I've already given you a lot to think about. So get up, stretch your legs, and I will meet you in the next video.